finger in the center of the lid, perpendicular, and then on the other side. Yes. And then push towards up.
That'll get me so far.
Towards
You gotta
yourself.
stay perpendicular to the lid.
Keep my finger perpendicular to the lid. Can anyone do it with less effort? Or describe how to do it with less effort?
Like if you do it the same way, but more up to, like, more up to his butt.
No, over here.
Uh-huh.
Let's say that works on our door. So you four will be able to see it, maybe Emily and Jennifer. So I put my finger on near the end of the door and push perpendicular to it. It's not closing.
Center of the mass.
Center of the mass. It's not working. For those who missed it, the door's hanging out like that, and you know, it's not a flat shape. I mean, there is some depth to it, more than something like this. So I push perpendicular, put my finger at the end, and I push perpendicular to it, and it wasn't closed. And then suggestion center of the mass, so I pushed there, didn't close.
Well, center of the mass going this way, like in the middle of the door. Yeah,
And that's gonna close it.
opposite side of the door. Just stay perpendicular to it though.
So finger stays perpendicular to the door. I'm on the opposite side. And how would I make it more efficient?
Move it. to
Where?
the- Move it to the furthest point away from the pivot point in the direction that you want to go. So,
All right, we'll end that. We'll end it there. But years ago, I did an exercise with students where I had them explain how to tie shoes. That took a half hour. Or some of the time was wasted as they were trying to decide the one rabbit ear or two rabbit ear method. All right. Let's think about what's required in order to be able to get that door to close. First, we're trying to, it starting at rest, and it's going to stay at rest unless we do something. So we're going to then apply an influence to cause it to rotate. That influence causing it to rotate is torque. Technically, it's the torque that causes the angular acceleration. So force is an influence that might cause acceleration. Torque is an influence that might cause angular acceleration. So we're applying torque. And it mattered, well, basically how much force do I apply? Where I apply the force. And the direction of the force. Those are the three things that have to be taken into account when you're trying to apply torque. And there's a nice, convenient, simple little formula which bundles all of that. As one professor called it, it's got conservation of complexity. The fewer letters, the more that goes into each letter. But torque, the symbol that we used before, is equal to R cross F. It's not F cross R, it's R cross F. The order matters. This is known as a cross product. There's two ways of multiplying vectors. One is the dot product, and we did that back when we were dealing with work, and this is the cross product. As the door was closing, so as this closes, what is the direction of the angular velocity? So like that, and it's closing like this. What's the direction of the angular velocity? All right, we seem to be starting to get a consensus here of some sort. Right hand. Yeah, there we go. Okay, think about where the hinge is. The hinge is along here. I guess on the box it's over here, but the hinge is running up and down. On the door, the hinge is basically vertical. So my thumb's either going to point up or point down. The direction that this thing is swinging is that way, down. So the angular velocity is down. What's the direction of the angular acceleration? Let's go back to, it starts at rest, then it starts to move. Is it speeding up or slowing down? So what does that tell you about the direction of the angular acceleration and the angular velocity? No, we haven't defined positive yet.
Yeah,
Why?
because
Same direction as velocity. If acceleration is positive, it should be the same.
if it's
We
speeding up.
still haven't defined positive yet. Pardon?
So it's speeding up, so it's in the same direction.
Yes. If it's speeding up the same direction as the angular velocity, just like with the linear stuff, if an object's speeding up, acceleration and velocity, same direction. All right, so my angular acceleration is down. Since torque, this is the total torque, is equal to I times alpha, if the angular acceleration is down, what's the direction of my torque? Yes, it has to be. I got only two vectors in this equation, they have to be in the same direction. All right. This, now the difference between these two formulas, this is you add up all the torques, you get this. This is an individual torque. Now, if I just happen to have only one thing doing any torque on it, causing any rotational acceleration, then they'd be equal to each other if I have only one. But let's think about all this right here. I've got R. Let's define what R is. R has a couple different names. It's called the moment arm, or the lever arm. It is a vector, thus the symbol there, a vector from the axis of rotation, to where the force is applied. So we, if we are looking at overhead at this thing, of course, put it down somewhere. I will risk the blisters. So overhead view. Stop it. this? No. Tools. That's it. What other settings? All right, it's working. There we go. All right, so I've got from an overhead view, and I had the box like that, looking down on it. R, if I applied the force here, if that's where I applied the force, R is a vector from the hinge to where the force is applied. This would be R. And that is F. So if they're perpendicular to each other, the magnitude of my torque, so if my moment arm is perpendicular to my force, the torque, magnitude of the torque is just R times F. So we'll deal with a lot of problems where they're perpendicular to each other. Again, side note, in general, the magnitude of the torque would be RF, sine of the angle between those two vectors. If you have enough drink, don't worry about it, side note. So, but we still have to somehow figure out what this cross product is. Torque is a vector, so there's got to be a vector in here somewhere, or a vector in the answer when I multiply these. So how do I get R and F and get them to indicate what would be into the board here? Down. Because again, overhead shot, down is that way. Well, when you're doing a cross product, I write the two vectors tail to tail. Force is pointing in that direction, R is pointing down. I did the same thing right there. And now we use the right hand rule. Since I'm doing R cross F, R comes first. I put my hand in the direction of R, which is down. I got 360 degrees in which I can have my hand. It's going down, and now I want my fingers to curl towards the second vector. So that means I have to point it this way because force is pointing in that direction, so my fingers need to curl that way. My thumb points that way, which would be down on that. So R cross F, the direction of R cross F is on this diagram into the board. There, down. So it all fits together. The torque is down, angular acceleration is down, the angular velocity once it starts moving is down, and it's just a mathematical convenience. When I was teaching this topic at high school, I happened to be driving along Bush River Road, Columbia, South Carolina, and there was a guy changing his tire. Couldn't have asked for better timing on my part. He was using a tire iron, trying to get the nuts off of it, and the tire iron basically was a long piece of metal, and there was a hinge here, so that, and I don't know why it suddenly changed colors there, but so that this could rotate. So you could also have it like at the hinge. You could have it like that. So he took this thing, and it was still straight, and he put it into the lug nut, and he was trying to rotate it like that, not having much success. I stopped and I said, and I saw what he was doing, and I said, I think it's supposed to bend. Because in this situation right here, the moment arm was basically that tall right there. That was the moment arm right there. seems to randomly go back and forth. So it's from basically the middle to where the force was being applied. And also the force was the friction from his hands onto the rod. So that's dependent upon how tightly he's gripping it, and depends upon basically the coefficient of friction between his hands and the rod. If you bend it like that, so now the nut is here, I can rotate it around like that. So having it bent, I can rotate it like that. I increase my moment arm. Significantly by bending it. I think that's where I left him after he got that, because I don't remember actually getting the tire off.
So really quickly, that's DIR for direction?
Yes.
Up at the top there, okay.
Yeah, there's no nice symbol, like for magnitude you just put absolute value symbols, but direction, there's not really a.
And for the right-hand rule for that, you had it so that you aligned your hand with
The first vector.
first vector and then moved it towards the second.
Yes. So in this case right here, we're looking at the box, R was a vector going that way. And the force I applied was that way. The thumb points down.
And the circle with X, if it was a dot, it would be up,
Right.
because it's going from there, is it going this way?
Correct.
Okay, and
Yeah. Because I basically took that view like that and I.
put it in here. Okay.
Questions?
Yeah, can you explain that again? The circle with the X and the circle with
Wait,
the dot.
that right there?
Yeah, how that works, or like how you got that.
Okay, so first off, I'm looking at it from an overhead point of view like this. So that's the viewpoint right there. As I'm closing it, we've talked about the fact that the angular velocity, the angular acceleration, the torque, all down. So we should, doing this cross product, we should get the same direction down. So R cross F, my R was this way, F was this way. So you put them tail to tail, put your hand in the direction of the first vector, because it's R cross F, so I do R first. And I want my fingers to bend towards the second one, which is that way. So R, F, my thumb points that way.
Okay.
Other questions? Ty?
And do you always put it into an overhead view in order to do that, or? Because if you're doing it on the, as it sits there, doesn't your answer change?
It would be down.
Right.
Yeah, it would change. So the answer to the original question is down, and I was hoping that by doing that,
yeah.
going that way is the same as going down in real life. Because this isn't real.
So it always goes from R to F.
Yes, R comes first. Suppose you did F cross R. What would you get? What would be the difference between R cross F and F cross R? That was the right approach, Jennifer. That was the thing you should have done. Did you get the answer of the difference? Yeah, it flips. F cross R points this way, R cross F points that way. For you math fans out there, the commutative property of multiplication does not hold with cross products. Which is why pushing on the door on that side gets me a different result than pushing on the door from this side. It's time to throw things. Sling things. How close am I? Well, worry about that in a moment. All right, got an ordinary stopper here that I'm going to swing around. I want to hit a spot on the board. I probably don't want to hit the electronics, so I will aim for this X right there. That's the spot. The circle is not indicating that something's into the board. I'm just circling the X that I'm going to try to hit. As I'm standing here, okay.
Should I move?
Not yet, unless you want to. That's how safe you two are both feeling. Okay. As I swing this around, the question is, where do I let go so that I hit the X? Now you're about to tell me, and potentially you'll have 9 different answers. So let me draw just an absolute spectacular model of the room. There's the X. And I'm swinging it around so that the angular velocity is pointing up or out of the board on this drawing. From the point of communication here, if I let go of it at this spot, we'll just call that 12 o'clock. If I let go at this spot, that's 9 o'clock, 6 o'clock, 3 o'clock, clock times. Where should I let go so that I hit the X?
3 o'clock.
Anyone else?
6.
6?